Aloha and welcome. In this video, we're going to be continuing on talking about binary search trees. So without further ado, let's open up the book. So binary search tree is a very useful form of the binary tree. And the binary search tree has an ordering property that says that each node's key is going to be greater than all the keys that you find in the left subtree and less than all of the things that you find in the right subtree. So let's go ahead and take a look here. We're going to click on Start, and it says the ordering property must hold for each node in the BST. Root key 4 is greater than left subtree key 2 and less than right subtree keys 6 and 8. So key 6 is less than right subtree key 8. So the tree is a BST. So when you look in here, you've got 4. 4 is going to be greater than 2. 4 is less than 6. Then in 6, 6 is less than 8. So this is valid. So looking here, node 5's left subtree has key 7. 5 is not greater than 7. So the tree is not a BST. So look at this. 4, 4 is greater than 2 and less than 6. That's correct. But then 6, and you look at the relation of 8. So you've got, yeah, so this is the one we just did. This one is correct. Then you look over here, since 5, 5 should be greater than 7. It's not, so this doesn't hold. So if this is over here in this side, that would be different, but it's not. So this is not a valid BST right there. So then node 6's left subtree has key 7, but 6 is not greater than 7, so the tree is not a BST. So 6, it's greater than 3 and less than 9, but 3, and 7, even though this part is valid, this invalidates because 7 is greater than 6. So last step here, we're going to be looking at this one. And so if you look at all the different keys in here, all the keys in all the subtrees obey the ordering property. So the tree is a BST. So all these are correctly. So if you look at the top, 3 is less than, 7 is greater than. Then you see it over here, it's preserved that way as 2. You look at 4, it's still less than 5, so it's right. Then these check out as well. So now we're going to look at exercises binary search tree basic ordering property. So do node 900 and the node subtrees obey the BST ordering property? So do node 900 and the node subtrees obey the BST ordering? So 900 here is so 850 is less than it, 950 is greater than it, and when you look at 850 and 950. It seems to follow everything here. That is correct. That is true. So we click on yes. Go ahead and do the rest of these as examples. So keep in mind here that BST's keys are distinct. You can't do it, when they're not distinct or they're not unique. But we're not covering that here in this book. So now we're going to look at a binary search tree search operation within the BST search, or we're going to look at a search operation within the BST. So binary search tree stores ordered information here. A linked list can also store information as a collection of values, but because of BST structures, operations like search, insert, and remove may be much faster than a linked list. And we'll show a little bit about this. Actually, this is, I believe, your assignment number 3 as well. I have you comparing the two. So given a key, a BST search operation returns the first node with a matching key, or null if no matching key is found. So each time the search compares the search key with an unequal node, the search need only continue down to one of the node's 2 children. So the search often visits only a small portion of the tree's nodes. So again, we just talked about visiting. So a BST search operation is set to visit a node if that node's key is accessed during the operation. So we're going to look here at our illustration. So BST may yield faster searches than a linked list. So you click on Go here. So if you're looking for 50, You're going to have to linearly go through this. Remember, this is a linear operation. You're having to go through here 5 times to get to 50. So with that, you're going 5 times. So if we're going to be using the balanced binary search tree, we go in here looking for 40, or I mean for 50. We compare it to 40, and we know that it's going to be greater than that. So we click on that. So we go down the right-hand side. We see that it's not 60. So yeah, so that one doesn't go. So at that point, we're going to be searching the left side because it's less than 60. And we find 50 right there. So we've gone through 3 searches here. So that's 3 comparisons versus 5 for the linear search. So searching a linked list for 85 requires visiting all 7 nodes. So if you're looking for 85 in there, you're going to have to search through all the nodes and not find it. But if you're going through the BST, the search for number 85 has you going through just 3 to find that it's not in there. So referring to the information above, searching the linked list for 20 visits how many nodes. So if you're looking for 20 up here, and you're going to wait, which search, searching the linked list. Okay, okay, if it's a linked list and we're searching for 20, we're using this one. So it takes us 1, 2 comparisons. So we're going to have to visit 2 nodes. Then searching the BST for 20 visits how many nodes. So if we're going to visit 20 over here, we're going to be visiting the first one and the second one there. So that's going to be 2 nodes as well. I think it's 2 nodes, yeah, or 2. Yep. So continue on going through all those. We're going to talk about successors and predecessors here. So a BST defines an ordering among the nodes from smallest to largest. So a BST node's successor is the node that comes after the BST, after it in the BST ordering. So in ABC, A's successor is going to be B, B's successor is going to be C. So the opposite of that is going to be the predecessor, and the predecessor node is one that comes before in the BST ordering. So if a node has a right subtree, the node's successor is that right tree's leftmost child. So it's going to be the leftmost child. So for D up here, its successor is going to be if it has a right tree, it's going to be the leftmost child. So F is going to be its successor. So F is the one immediately coming after D. Okay. So if a node doesn't have a right subtree, the node successor is the first ancestor having this node in the left subtree. Another section provides an algorithm for printing a BST's node in order. Great. So let's go and look at our participation activities here. So the first node in the BST ordering is 150. So first node in the BST ordering is 150. So where is 150 in here? Is this true or is this false? So the first node in BST ordering is 150. So 50, we're going to go down the leftmost, and we're going to find that it is indeed 150. So 150 successor is 250. So if we look at this, we go down to see what is its successor, what is the very next one. And indeed, we're going to find that 250 is the next one. So 250 is the next larger item. If a node has a right subtree, the successor is the leftmost of that one. So this is going to be, it has the right, and it's going to be the leftmost here. So that's going to be the 250. So go ahead, look through all the rest of these on your own. The last exercise here is challenge activity. You look in here and say, does node 26 and the node subtree obey the BST ordering property? So look at 26, and does it obey the BST ordering property? What is that ordering property? The ordering property is that every order in, or every node to the left of it, you're going to have a number that's less than, and to the right of it, you're going to have a number that's greater than. And that is true for each node and its descendants all the way down. So you'll want to make sure that when you look at this, 35, okay, 35, this is 35 is going to be greater than 26. That is true. And 26, the numbers on the left are going to be less than 26. The numbers on the right are going to be greater than 26. So you'll need to go through all these and answer the questions accordingly. So anyway, that's the rest of our section there. So go ahead, look through it again. Know a couple things. Know that there's an ordering to your binary search trees. Then the root node is going to be greater than the left node and less than the right node, and it holds true for all the subtrees. And then the other thing is that BST keys are distinct here, and the term visit, where we visit if we go through that on a if it's accessed during an operation. Note that binary is much faster than linear searches for most cases. And we have the concept of successors and predecessors and an algorithm to find the different successors and predecessors for them. And that's it. If you have any questions, feel free to reach out and ask me, and I'll be happy to help you. Other than that, have a great day. Aloha.